All right, I guess I'll get going now, everyone. Thank you very much for coming to this seminar. My name is Rick Lumpkin. I'm here in the Physical Oceanography Division, and I'm the drifter guy here at AOML. So obviously, I love working with these data. I'm going to be looking at drogued and undrogued drifter data to understand better surface pathways, and I'll motivate that in a review of some previous publications up front. So the drogue is the sea anchor that's attached to the base of the drifter. Here you see a drifter lying out, and I'm posing way back there at the back of it. Here's the surface float. There's this long tether, and it's connected to the drogue, which is centered at a depth of 15 meters to follow mixed layer currents. It's about 10 meters long, and basically the cross-sectional area of the entire instrument, 40 times this is the 40 times the cross-sectional area of everything else. So it dominates that kind of cross-sectional area of the instrument, determining or making sure that it will follow the mixed layer currents. And as long as it's attached, the motion relative to the currents at 15 meters, which we call the slip, is less than a centimeter per second in 10 meters per second of wind. And that's been measured by attaching an 80 CP to the drifter. They typically lose their drogue after around 200 days. The drifters themselves tend to live about 450 days, which means that there's a lot of data in our archive that's collected by drifters which have lost their drogues. About half, it works out to be. There's a number of different reasons why an undrogued drifter would move differently from a drogued drifter. First of all, the currents right at the surface can well be different than the currents at 15 meters depth. But then there's also the possibility of direct wind forcing. When the drogue is attached, the surface float actually gets pulled underwater very frequently. It spends more time underwater than floating at the surface. We know this from basically satellite fixes. And we used to also have submergence sensors attached to the instrument. So when it's lost the drogue, it's much more buoyant. And that sphere is floating up at the surface and being blown directly by the wind as well. And because it's also sitting right at the surface, it's a lot more subject to Stokes drift and even surfing and breaking waves. So the waves can move it much more quickly. So there's all these different effects that cause a surface float without the drogue attached to move differently than a drifter that has that drogue attached. Or to kind of summarize in the columns, the drogue drifter, most of the area is at 10 to 20 meters depth, following the currents at 15 meters. It's similar to the way nearly neutrally buoyant object in the kind of mixed layer is moving around, or a water parcel itself. So perhaps like weathered oil that's become relatively neutrally buoyant would move like a drogued drifter. And we know that the downwind slip is about 0.1% of the wind speed. Undrogued drifter, the instrument is entirely within the upper few centimeters of water. It follows a combination of wind, waves, and currents. It's similar to, say, a piece of floating debris would move. Is similar to how a surface float without the drogue attached is going to move around in the water column. And we know from studies like this one, this is Lorindo et al. 2017, where we mapped out the mean currents of drogued drifters and of undrogued drifters, and then compared that to the wind speed to see what additional factor of the wind speed would match them up. And we found that this distribution went, here's 1% of wind speed, here's 2% of wind speed. And these are all these different global bins. You can see there's a kind of interesting looking distribution. Here's the color scale again from 0.5 to 2.5. So there's some odd structure in there that we need to understand. But in general, it's about 1.5% of the wind speed is this additional downwind motion of an undrogued drifter compared to a drogued drifter. There have been a number of previous studies of surface transport using drifters, and a number of approaches taken in those studies. Looking at trajectories, using the transit matrix approach that I'll be talking about, and then advection diffusion kind of studies. I'm not going to get into that third type very heavily at all. I'll mention one very prominent example is this 1990 paper where they use ship drift velocities rather than drifter derived, but basically it could be drifter derived if you wanted to. So you take a velocity field, you put a simulated particle in it, and you advect it in that field. You can release 100 million simulated particles if you want. You can simulate the turbulence of the field through a Lagrangian stochastic model, or explicitly if you have, say, a VSO altimetry resolving eddies. And you could even include a downwind motion if you want. You know, this additional downwind that object sitting right at the surface would go. And that's a very tunable kind of model. So it can be far removed from actual observations by the time you have all these additional factors built in. The trajectories in the transit matrix approach, however, are based on actual observations much more directly. Trajectories kind of speak for themselves. This is when anytime you approach a problem using the drifter data in terms of like the downstream fate or the upstream source, it's the first thing you want to do. Here's a very prominent example of Brambilla and Talley, 2006, where they wanted to see what connectivity there was between the subtropical and subpolar North Atlantic from these drifter trajectories, drogued only. All the ones that pass through that green box, there's subsequent downstream trajectories. And you can basically see from, and as they concluded, there's very little evidence right at the surface that the water is basically moving from the Gulf Stream along the North Atlantic current and up into the subpolar North Atlantic. In fact, only one drogued drifter in the entire data set did that. Now, this approach is extremely straightforward because you're using the in situ observations. You know, there's no assumptions you're making here. But there is a weakness, a significant one, and that is that the drifters lose their drogues and they die. And so as you go forward in time, the statistics become less and less robust. Basically, you end up, if you 2 years later, there may be only a very, very small number of drifters still alive from this source region. Brambilla and Talley went around that, or tried to somewhat alleviate that problem by creating composite trajectories. So what they did is they took these trajectories, and when the end of that came within a certain distance of another trajectory, they could continue the trajectory, and basically a two-drifter kind of super trajectory. And so when I flip back and forth, you can see how that added to the data set of trajectories here. So that helps make things a little more robust downstream because you effectively simulate drifters that live longer this way. But you have to be careful. For example, you want to make sure that you're not jumping from one side of the Gulf Stream front to the other if the front is moving north to south. They did that by also requiring a delta T criterion on whether they would join up trajectories or not. Then there's a transit matrix approach, which is one step further removed using the statistics of the drifters. So I'm going to show you an example of how this calculation is done, first of all. You divide up the world into boxes. And in this case, I've done 1 degree bins for this example. And then you find all the drifters that ever entered or passed through or were deployed within this one bin. And you look delta T later, 30 days in this example. 30 days later, the drifters that were in that box, see there were 260. 235 drifters were still alive 30 days later. And that's where they were located. You then calculate within your 1 degree by 1 degree bins, what are the odds that starting here, you end up in all of my other 1 degree by 1 degree bins. And here's the probability cloud in percent, 1%, 1.5%. Basically, in this particular example case, when you sum all those probabilities up, you get a 90% chance because about 10% of the drifters died. But you could always renormalize that if you wanted your tracer to be conserved. So in other words, you could normalize it so that the sum is 100%. And then you could take another step, and another step, and another step, and keep propagating this probability forward in time. And you can basically then simulate where drifters would go starting from an original spot. Or you could go backwards in time. You could always say, where were they 30 days ago? And you might find that you have, in this particular example, what did I say? I said, yeah, there are 260 drifters. So maybe I go back 30 days, and I find 235 drifters. So, little quiz. How is that? How would there be less drifters 30 days ago? Yep, thank you. The reverse of dying, deployments, drifters that were deployed less than 30 days ago that ended up in that box. So again, you want to probably normalize that probability unless you care about a statistical simulation of drifters being deployed, which likely you don't if you're approaching this from most of the kinds of problems I'll be showing you. So we use the transit matrix approach, for example, the Global Drifter Program does, to make a 90-day forecast of where we're likely to have drifters. This shows you December 17th, the odds from 0 to 100% that there'll be a drifter within 5 degrees of every point. And all I'm doing is taking the current locations of all the drifters and propagating that probability forward 90 days in time. Now, the strengths of this approach is that it's based on the real statistics of in situ drifters. And as you move forward in time, it becomes more and more robust generally. Because you're moving to as the cloud is getting larger, you're going from the statistics of maybe 200 drifters in that box to 2,000 drifters in the next time step, to 200,000 drifters in the next time step. So you're getting more and more statistics of more and more drifters as you propagate forward in time. But it can be noisy in places where you have very few observations. Here is the first really prominent paper that used this transit matrix approach for a problem. Maximenko et al. 2012 wanted to see where in the world is debris floating at the surface likely to accumulate. And they calculated this transit matrix using all of the drifters, drogued and undrogued. Their justification for this is based on two things. One, very pragmatic. You want as much statistics as possible in this. You want as many drifters as possible. So you basically double your data set by using drogued and undrogued. Two, they argue that they're interested in things within the entire upper water column, both following the water at about 15 meters, relatively neutrally buoyant objects, in other words, and things floating right at the surface like undrogued drifters. So by using the statistics of both drogued and undrogued, you're basically trying to simulate all sorts of things that are floating at or near the surface. And as I run it forward in time, you can see they start off with a homogeneous distribution, run it forward 1 year, 3 years, 10 years, and this is, I believe, a log 10 concentration. I will definitely be showing that in the simulations I've done, and I'll explain the color bar a little better. But the conclusion that they came up with is that there are 5 gyres, 5 trash gyres, where the objects will tend to accumulate within the oceans. You can see the North Atlantic and South Atlantic gyres, the North Pacific and South Pacific, and the Indian Ocean gyre. Now, this is a homogeneous release, as I mentioned, and they did not normalize. They didn't conserve the probability as they move forward in time. So drifters, or the concentration is being removed where drifters die, where drifters run aground, and where drifters get picked up by fishermen and such. That's not ideal. So I forgot to mention, so yes, they basically show if you're in one of these 5 areas, you end up in one of those 5 trash gyres. So that's not ideal, though, that the statistics are following drifters for all these cases, because marine debris isn't getting picked up at the same rate that drifters are. They're not as interesting generally, and certainly not quitting transmitting. So we want to not do that. So what we did in this study was to look at where drifters are running aground separately from the other causes of death, and then rerun the Maximenko et al. Simulation, but only allowing for the running aground, which marine debris presumably can do. That way we can not have these deaths for other reasons, and we can see what regions are most likely to have to be exposed to marine debris running aground. And that's the vertical bars in this plot. And then you see the concentration 10 years later, and you can see there's some slight differences in the magnitudes and the intensities of these different trash gyres compared to the Maximenko et al. In particular, the South Pacific one is extremely strong in this simulation. But most debris is not released in the southern hemisphere. It's certainly not released homogeneously. And so von Sebille et al. Took this a step further by, in this case, it's a transit matrix, again, from all drifters, drogued and undrogued, conserved. And he started off with a concentration that was, the distribution was set by population density along the coastline. And it was tuned to match an estimate of how much plastic was dumped in the ocean globally in 2010. So that the total amount of debris, starting the simulation, follows the population densities on the coastlines and matches that amount. They run it forward until it's effectively a steady state, and they end up with, rather than arbitrary dimensionless units, they end up with microplastic mass or microplastic counts, which is something that can be compared directly against observations. And one of the great mysteries of this paper was that comparison of these in situ samples. Those samples tend to be like 1% of what the simulation indicated. So there's a huge mismatch that we haven't completely solved yet. Eric von Sebille thinks that one thing that's really, really bad is this estimate, that it's probably grossly large compared to reality because it's based on one particular site that wasn't extrapolated to the entire world. But another possibility, of course, is something else is removing the plastic from the ocean, ingested by marine organisms, a significant amount washing ashore that he didn't include in this simulation, or other things. Now, in this study of 2016, Vera et al. Looked separately at drogued versus undrogued drifters and where they accumulate. And they noted, first of all, if you take the initial the concentration of all the drogued drifters and you look a year later, and you kind of take a difference, versus undrogued drifters a year later, you find that the undrogued drifters accumulate much more rapidly in the centers of the gyres. And this paper also argues that the accumulation is not just from the equine convergence, that's a much slower process driving the drogued drifters, but it's also due to the finite size of the objects and inertial effects of wind and current forcing. It suggests, in other words, that we need to be a little careful and not just throw all the statistics into the hopper and basically not pay attention to the differences between drogued and undrogued.
Can I ask you a question?
Sure.
What does that mean, inertial effects of the wind and currents?
Effectively, that the forcing of the wind and currents on the object creates a force that ends up being directed towards the center of the gyre on gyre rotation kind of time scale. Is not we're talking very, very subinertial. I'll give you a copy of the paper. I'm not 100% sure that I buy it yet, but it seems to be consistent with the observations, and so it does seem to be that this direct forcing effect of, say, the wind blowing on the buoys has a significant effect, as well as just this downwind effect and an equine convergence. So we need to reassess these earlier studies and to understand the difference between drogued and undrogued statistics and what those implications have for the conclusions that those studies have reached. So what I've done is I've recalculated the transit matrix for, again, all drifters. That's been done before. I'm not going to show a lot of those results here. But separately, only for drogued drifters and only for undrogued drifters. And we'll redo some of these previous studies. And I did the transit matrix calculation on a 1/2 degree by 1/2 degree grid for a time step of 15 days. And if you're wondering how long that takes to crank through the entire drifter data set, it was about 5 days to calculate this transit matrix for these 3 cases. And then once you've done that calculation, you can do the calculations I'll be showing you here of iterating that matrix in a matter of seconds. So if someone here were interested in what if something was put here, where did it come from, where did it go to, I could literally get results within 10 minutes. It's very, very fast once you have the matrix calculated to run the matrix to do these kinds of simulations. So let's look at a homogeneous release, similar to the Maximenko et al. Study, but only use the Drogue on data and integrate this for 10 years and conserve the tracer. Here's what we get. Now what you're seeing is log 10 concentration. So that's 1, 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, 10 to the minus 10. And effectively it's normalized so the sum is 1. And so after 10 years, there's our concentration for the drogued drifter data, looking somewhat similar to what the Maximenko et al. Study showed. We're seeing a very strong gyres of relatively large values of concentration around 10 to the minus 3 in those 2 gyres of the Indian and South Pacific, and the others somewhat weaker. But if we do this, oh, and by the way, you also see some kind of noise down in this area. That's because there's not an awful lot of drogued observations there. By the time drifters reach that area, they tend to be old, they tend to have lost their drogues. And so it's actually mostly undrogued drifters that sample that part of the ocean. That's why it's so important to slip correct, if you can, to calculate mean currents, like in Lorenzo et al. So here's the same thing, but for the undrogued drifters only. Again, running out 10 years. One of the things that's really dramatically different is what's happening in the Indian Ocean. In the drogued case, there was quite a bit of accumulation in that Indian gyre that in this case is actually leaking around and entering the South Pacific gyre or following the Agulhas pathway into the South Atlantic, which you can see is stronger in the undrogued case compared to the drogued. But there's virtually no Indian gyre for the undrogued drifters compared to the drogued drifters. If we take a difference, this highlights that. So this is a difference in concentration after 10 years. Drogued, red, undrogued, blue. So you don't see an awful lot of difference in the northern hemisphere between the 2 cases, but you see a really big difference. Basically, there is little to no Indian Ocean gyre for undrogued drifters, which I remind you float like marine debris that is buoyant, floating at the surface of the ocean. It's a 4 gyre situation for that sort of material. We see a shift in the location of this gyre, with a lot more undrogued drifters tending to accumulate there, being fed by the Indian Ocean gyre, and more undrogued drifters accumulating in the South Atlantic compared to drogued drifters, again fed from that Indian Ocean gyre that does not retain them. Let's look at the North Atlantic and zoom in on that. What I'm going to do is, again, run things forward in time. It's going to be conserved. I'm going to release it right here off of Florida. And we're going to see where it goes. It's pretty much reached a steady state already at this point. So you can see that it accumulates in sort of the southern part of the subtropical gyre, all across the entire ocean basin, but shifted a bit to the east, so that it's actually, there's still relatively high concentrations, relatively close to Europe and Africa. And you saw the speed of that. Let me rerun that just again. Watch the speed that it's accumulating there. 1,500, 600 days. So 1,600 days, pretty much, you've reached close to steady state. Now look at the undrogued drifters, same thing. Very rapidly reaches a steady state at 900, 1,200. There's a bit of sloshing, but it's already basically reached the center of its center of attraction. It's pretty much steady state now. And you can see the location shifted compared to where the drogued drifters tend to accumulate. So as Baranvero et al. Concluded, it happens faster, and it's also, we see here, shifted. There's drogued, undrogued. You also see some tendency for undrogued, even though they're very low probabilities, but slightly better chance than compared to drogued of actually getting to the southern hemisphere. And when we take the difference between the two, again, red is drogued more likely, blue is undrogued more likely, and we can see that the drogued center of mass has shifted south and east, the undrogued center of mass shifted north and west. So again, why does this matter? Well, if something is moving, like basically neutrally buoyant at the upper mixed layer, it'll accumulate this side of the Atlantic a little more likely compared to objects floating at the surface exposed to wind forcing and wave forcing as well, which are going to be shifted towards the Sargasso Sea more. This was a paper by Van Sebille, Beale, and Johns looking at connectivity between the Agulhas and the North Atlantic. So they took the drifter observations. They did simulated drifter trajectories here, which is sort of like you take the PDF of that transit matrix, the probability distribution function, and you collapse that to have a single simulated trajectory, and you can do that thousands of times. And that's what he did, or what they did in this study, is release thousands of simulated drifters right here in the Agulhas and see how long it takes them to get up to the North Atlantic and what pathways they take to get there. The paper didn't say whether they use all data or drogued or undrogued only, so I had to take this figure here and compare that to my calculation of how many observations do we have total versus drogued, and it was obvious, they matched up perfectly. It's all drogued plus undrogued. So they were using a mix of the two, and we can ask, well, okay, are there significant differences if we look at drogued versus undrogued released in the Agulhas? And that's what you're seeing here, some snapshots of the simulation. So I have released it in the Agulhas right about there at the very edge, and now we're running forward separately drogued and undrogued. And what you can see after 1 year already is a big difference in how quickly things are going to be reaching the North Atlantic. The drogued data is not yet reached the South American coastline here, whereas the undrogued data has reached it and is actually having some probability now in the North Equatorial countercurrent penetrating into the North Atlantic. After 3 years, when the drogued drifters are just starting to reach South America, we now have some probability. You're not seeing very well, and it's very low probability, but you are finding some that are actually starting to go into the Gulf Stream system here. And then after 5 and 50 years, yeah, that really light blue is not showing up as well as I wish it was, but effectively it's much faster and much more easy for the undrogued data to have some probabilities, albeit very low, into the North Atlantic that's not present in the drogued drifters. So this suggests to me that there would be a pretty significant difference if you separate those statistics for something like their arrival time plot that you see in the bottom right. And I could calculate something like that by basically drawing a similar line to what they did and then just seeing when the concentration is arriving at that line. Here's another interesting problem that became controversial because of the way people approached the problem. The Malaysian Airlines flight, MH370, which disappeared on the 8th of March. It was supposed to be traveling along this red line, picked up on a military radar traveling through along this pathway to that point, and radar no longer tracked it after that. However, there were automatic Inmarsat fixes which suggested that the final location was somewhere along this arc in the South Atlantic. Here's Australia. And given this information, the search efforts for the wreckage shifted from these areas up here off of Indonesia and Malaysia to search area along this arc in late March, basically, of that year. And then 500 days later, a piece of debris washed up on La Reunion Island here that was positively identified as from that airplane. More debris that was found subsequently, but that was the first identified piece of debris from this plane. And so basically people said, okay, if it took basically kind of a southerly path, we intercept with that arc, then this is kind of the most likely area, and that's where the search operations had shifted to already at this point. But this created some immediate controversy. There was a group of oceanographers at GeoMar that took a computer simulation with very realistic ocean currents. I suspect calibrated to match the drifters, but I don't know that for sure, the drogued drifters. But for sure, when they basically ran it backwards from La Reunion 500 days, they found this cloud of probability of where the crash most likely happened that was considerably to the north of that search arc area. And they even made statements to the effect in the press to the effect of they felt very sorry for the families of these people, that the search effort was obviously happening in the wrong place. This was backed up by calculations being done by a statistician named Brock McEwen from Canada, who used a couple of different products. Scud is tuned to fit the drifter observations. Adrift is actually using the drogued and the undrogued drifter observations, and did a lot of different statistical simulations and said it's extremely unlikely that the crash happened here. It's much more likely that it happened up here for the debris to end up there. And if it had happened here, much more of the debris would have washed up in Australia. Now, Trinanis et al. 2016 approached this by going back to the basic data itself and saying, look, we believe that the debris will move most likely like the undrogued drifters, right? The drogued drifters are sort of irrelevant to something floating at the surface being blown by the wind. And if you look at all of the undrogued drifters that pass through here, you find a very large fraction of them, the red ones, that subsequently go through that purple box in the area where the debris washed up. So we already kind of know what the answer is going to be. The answer is going to be that those previous conclusions were because people were looking at currents that were better representative of something floating at 15 meters depth and not floating at the surface. But we can verify that with some simulations. So what I'm going to do is a backwards simulation. I have to have a seasonality caveat here. I'm using all the data from all time. I'm not using particular months. And of course, this is a region with very strong seasonality. One could, in principle, calculate this for different seasons and then run it backwards from a particular month. That would tend to make less spread probabilities. That, in fact, is going to reinforce the point I'm going to make, however, because what you're going to see spreads out the probabilities more rapidly than such a more ideal simulation would be. So here we are, drogued drifter data, ending up at La Reunion Island, and now we're going to go backwards in time 500 days. The black contour is the 95% contour. There's a 95% chance that the object is somewhere inside that contour. The red contour is the highest 50% chance. So it's encircling the highest probabilities, and there's a 50-50 chance 500 days earlier you originate from that area. This is completely consistent with that GeoMar study. This is consistent with what that statistician was finding in his examination of ocean currents and simulated advection of debris. And it's completely inconsistent with that search arc. But we did the same exact thing with undrogued data, and that's what we find. right in that arc. The arc cuts right through the highest probability that the debris originated from that spot. We can do this the other way as well. I remind you that the statistician said that if the debris was released here, more of it would have washed up on Australia than over here in La Réunion. I believe that especially the adrift study he was using, but also SCUD, which is based on a mix of drogued and undrogued. SCUD was supposed to be using only drogued drifters, by the way, aside here. But Maximenko calculated the SCUD model before we did the drogue reevaluation, where we realized a lot of drifters had lost their drogues, and we didn't recognize that properly. So it is effectively a mix of drogued and undrogued statistics. Similarly, the adrift model that van Sebille put together is a mix of drogued and undrogued drifters. So this isn't going to be completely consistent, but this does show us separately what happens now if we release at the most likely spot and we run forward in time with only drogued drifter data. And indeed, the drogued drifter data are going to show an awful lot of running agrounds in Australia. Pretty high concentration values, pretty consistent with seeing a lot there compared to way over on the other side of the Indian Ocean. And when we do the same thing, running forward for 500 days with the undrogued drifter data, that's what we get. Perfectly consistent with running aground La Réunion, Madagascar, Mozambique, Tanzania, and if you go further in time, South Africa, where a piece of debris was discovered another 100 days after that. So yeah, it looks like these different studies made implicit assumptions, explicit in the case of Trinanis et al., but implicit in those earlier ones that ended up affecting their results very significantly because of the difference in how drogued versus undrogued drifters move around in the ocean. And then the final study I'd be talking about here is one work I'm doing with Libby, looking at the Sargassum inundation of 2011 to 2012. You can see some pictures from late 2011 of the Sargasso washing up on beaches and creating this enormous mess. This was happening in the Caribbean. This paper by James Franks et al., 2016, used drogued drifters only. They explicitly said we want to use drogued drifters to understand what the ocean transport will be of particles in the ocean. And they traced them back in time, or they traced out the pathways that would connect to the Caribbean and concluded that most of the debris must have come from this North Equatorial Recirculation region in ERR, and that there were no connection pathways between the Sargasso Sea and the Caribbean Sea. That the drogued data effectively said the ocean would not carry things from A to B. Put another way, they looked at all the drifters that were released here, and none of them went into the Caribbean, and all the drifters through here, and quite a large number of them entered the Caribbean. So they concluded that that's where the Sargassum must be coming from. Drogued data only, backward simulation. I'm going to start, or end, I should say, I'm going to end here in the Eastern Caribbean, and I'm going to run backwards in time. Drogued data only. And going that far back in time, we see a lot of connectivity, and you saw much more of it earlier in the movie, with that NERR region, and then way back in time, going back to probably that's 5 years, you see a connection to mostly the eastern North Atlantic, and really, really low values in the Sargasso Sea. It's consistent with that Franks et al. Doing the same thing with undrogued data only. Very rapid connection to the eastern subtropical and tropical Atlantic, and eventually throughout the subtropical Atlantic, including the Sargasso Sea. So let's look at some snapshots from this. We end up there, but a year and a half earlier, we would find that if we're looking at undrogued drifter data, it came from this region in the far eastern North Atlantic or South Atlantic, and that would move into the Caribbean in that amount of time, which is, by the way, the average lifetime of a drifter. Average lifetime of a drogue drifter is even less. It tends to lose their drogue sooner than when they stop transmitting, by the way. So somewhat earlier in time than 1.5 years back, you would basically see what Marks et al. Concluded, that something in the Caribbean would have originated from this region or maybe the southern part of the tropical Atlantic, but not strong evidence that it came from this part of the eastern tropical Atlantic or subtropical Atlantic. Libby has pointed out in her seminars that there was a very strongly negative phase of the NAO during the winter of 2009 to 2010, and that could have driven debris, or excuse me, that could have driven sargassum to this region right at about the right amount of time for it to then end up in the Caribbean. So the statistical model that I'm showing you here, I remind you, doesn't have, it has all of the data. So it would include the data from those anomalous years. It would include data from regular years as well. It's not going to know that maybe an event happened to rapidly push things to here, but given that, it does tell you under more climatological conditions, there's a very high probability that something here will end up in the Caribbean if it moves like an undrogued drifter, but not if it moves like a drogued drifter. So that brings me to my conclusions. Drogued and undrogued drifters move very differently. As a consequence, their upstream and downstream fates can be radically different, and we have to take that into consideration and see which one is most appropriate to the problem at hand. For quite a while, undrogued drifter data were sort of treated as noise, as trash that were discarded. People tended to just want the drogued drifter data and basically use that subset of the data to look at things like how water is moving around in the ocean. Then, Maximenko and von Sebille started saying, well, if we want to consider things floating as well, like marine debris, that data is probably valuable too. And they threw everything in, drogued and undrogued. So what I'm basically saying is, great, we're getting value out of those data, but let's consider how they move separately when we conclude things like where the debris that washed ashore on La Réunion came from 500 days earlier, and which one is most appropriate to the problem. The drogue drifters indicate 5 global trash gyres, and all the data do, because the drogue data do. But the undrogued drifters really have only 4 centers of attraction that are particularly significant. They don't show that Indian Ocean gyre. In the subtropical North Atlantic, the undrogued drifters accumulate more rapidly, and they accumulate in a different place, shifted more towards the Sargasso Sea, while the drogue drifters accumulate shifted off to the east and south of that region. Undrogued drifters also indicate faster connectivity between the Agulhas and the North Atlantic compared to drogued drifters. So conclusions, if you're really interested in how the water is moving from the Agulhas region into the North Atlantic, you really want to look at the drogued drifters, not all of the drifters. Drogue drifters that end up at La Réunion most likely originated from the central or eastern equatorial Indian Ocean, very far from the search area indicated by the Inmarsat fixes. However, as Trajectories et al. Concluded in their 2016 paper, undrogued drifters indicate something very different, completely consistent with a 500-day propagation from the most likely crash site to where that debris washed up in the right amount of time. The problem, at least in the simulations I've done, is that the 500 days allows that probability cloud to expand so much that it's not particularly helpful in narrowing down the site. Now, maybe if you could take that probability map and that probability, I've seen probability heat maps from the Inmarsat fixes, and if you convolve those two, maybe you would improve your chance of knowing where to look for the crash site. And that is, as we like to say, work that extends beyond the scope of the current study. But I would love to convolve those two probability maps and see what it shows us. Drogue drifters are not consistent with the sargassum moving from the eastern tropical Atlantic to the Caribbean, as Franks et al. Concluded in their 2016 paper. They instead suggest that the sargassum inundation must have originated from somewhere in the kind of southern tropical North Atlantic to this north equatorial recirculation region. But that's what drogue drifters show us. Undrogued drifters can definitely and will statistically transit from the eastern subtropical Atlantic to the Caribbean in about a year and a half. That's the kind of climatological state. And if we go back further in time, we find trajectories that could have originated from the Sargasso Sea that end up in the Caribbean using undrogued drifters. Now, there's a fair question. What moves more like sargassum, drogued or undrogued drifters? Drogued drifters, remember, are following the flow at 15 meters deep. Undrogued drifters are right at the surface, like sargassum, but unlike sargassum, they extend up above the surface and are exposed to the wind forcing as well. So presumably, sargassum moves different than both. And that is the final conclusion that I'll close this talk with, that in reality, a lot of objects may float something in between. Maybe they're going to, like for example, an Argo float sitting right at the surface. It's going to be extending, it's going to be mostly beneath the surface of the water. It's going to be the upper meter of water. So it's not going to move like to the 15-meter deep water, but it's also not going to have that wind forcing of a drifter floating right at the surface. Another example is if an object's buoyancy is changing with time. You can imagine a situation where it might start off moving more like an undrogued drifter, and then as it becomes more neutrally buoyant, starts moving more like a drogued drifter. So these kinds of simulations that I showed you here are fixed in time. They're fixed by the actual observations, and you can't really tune it to be something in between all that easily. But what you can do is you can take an advective diffusive model, and you can test it in these limits, and make sure that what you're getting is calibrated and validated against these sorts of probability calculations. And then you can basically do situations that are in between the one and the other. You can, for example, run a realistic simulation of oil that starts off very positively buoyant and then becomes more neutrally buoyant with time. Progress has to be made by examining different objects of shapes and sizes. And that's basically what we're doing with these special AOML tracer drifters that we've built and deployed, including some that are built to simulate sargassum itself, floating right beneath the surface. We have a large number of them out now, and the work is underway to examine how they move compared to the currents at 15 meters depth that we know from the drifters, in a number of cases that were deployed alongside those. And we can also see how things like the shape of the object, its buoyancy, and other factors affect how they move, what their effective windage is, the effective slip compared to 15 meters, and then hopefully be able to do more realistic simulations of how debris and sargassum and such floating at the surface is moving around in the ocean. That's all I have to say. Thanks for your attention, and I'd appreciate your questions.